Greetings, it's Mr. Burkhart here to talk to you about this week's lab. Following this clip, you will see me demonstrate the lab for you and share the data with you. So we've got a couple of pictures here. It'd be really helpful if you watch the Khan Academy videos for the week first. Those people are doing a really good job of explaining harmonics, resonance, and why you only get certain frequencies to resonate in tubes and on strings. I watched the videos. I thought they did a really good job. I don't really think it would bear repeating for me, though I'd be glad to hang out with people in a Zoom or a Google Meet or whatever and talk about things you don't understand. So the top picture is showing you a tuning fork resonating air in a pipe. So you can see that's what's happening physically as the air is being agitated and you get these compressions and rarefactions. Another way to model that wave is the picture on the left, which is showing you how the air is being, they've modeled that in the video and they show you why that model works. And you can see that there we have a wave coming in and then there's a node because it's not going to move when it hits the water at the bottom of, so this is basically a pipe with water in it that we're using. I'm sorry, we're going to have a pipe that's submerged in water. And we're going to lift the pipe out of the water and we're going to hold a tuning fork over it. And we're going to figure out where the spot is where the tuning fork will resonate and hum. It'll be really loud. And if we know that spot, we can use that to do different things. Back in the day, we used to calculate the speed of sound because there wasn't any way really I could hide the identity of the tuning forks from the students. So we found the wavelength and we found the frequency. We're not doing that in this lab. I thought it may be a more clever thing to do, since we all know what the speed of sound is anyways, or we should know that it's about 343 meters per second, that I could make this a lab where the tuning fork frequencies could be a mystery to you and you would have to try to determine their identity. So that's what you're going to do. You're going to watch me ring a tuning fork over some tubes and lift the tubes out of the water until they harmonize or they resonate, and then we'll use that length of pipe. So basically, once we know how long the pipe is that's resonating, we know from watching the Khan Academy videos that the length of a pipe that's got water and wind in, that's just blocked, not open on both ends. So there's open on both ends is different, but if it's blocked on the bottom, it's a fourth of the wavelength. So 4 times the length of the pipe is equal to wavelength, long story short. If we know the wavelength and we know the speed of sound in the air, we should be able to calculate the frequency of the tuning fork. And that's what I want you to do. This lab is not going to be due for a couple of weeks. I want to give you a week to work on it, and then it'll be due the following week, because in class, we're going to do the percent error together in class. The second week, I'm going to give you the identities of the tuning forks so you can see how close you got, and then we can work out what your mistakes might have been. If you should be able to get, well, if you could actually see the numbers really clearly yourself. I know that it was hard for me to get the camera completely focused down there in the tube. And so there's going to be some error, and you're going to have to do the best you can to figure out what that distance is. And I did kind of call out roughly what they were to give you an idea so that you could kind of estimate. All right, so that's what we're doing for the lab. Thank you. Good luck. Okay, here's another view of the lab from far away. Barely raise it up. Comes a little bit farther out of the water. More out of the water. I didn't pick a little bit bigger one, or my ruler wouldn't have been long enough. Take 3, resonance tube lab. I'm going to start with a small tuning fork. I've got a PVC pipe and a graduated cylinder with water. I put 1 drop of blue food coloring in it so that there was some contrast. It may be hard. You're going to have to estimate Make sure you're using the centimeter side over here. And what you need to do is mark the level at which the resonance happens, and I'll call it out. I'll say, yeah, we're there. You'll probably be able to hear it. And we need to do the best we can to see what the distance of the pipe is. The ruler does start right at 0 at the top of the pipe. And so this, if we could see it, if you could see it. All right, so I want you to try to see it. Let's go. About right there. Try it again. This is the small fork. It's just below 15. Maybe 15.2 or 3. Here's the next biggest fork. And right there. Maybe around 17. Here's the second to largest fork. And right there. Somewhere around 22. Actually, it's more like 23. Here's the big fork. Like 29.5. All right. Hello, it's Mr. Burkhart here to talk about the other part of the lab that I would like you to do. So in the first part, you're going to watch a video of me collecting data and use that data to calculate see if you can identify the frequencies of the tuning forks. I'd also like to see if, I would challenge you to see if you can reproduce this lab in some way in your own homes. And what you would need to do the lab is some sort of pipe, like I just found a piece of PVC pipe. I would ask that you not go spend a lot of money to do this. It's not really worth it. But if you happen to have any sort of pipe or any tube at home that you could use that's similar, the one I have is about maybe it's an inch in diameter. You don't want anything bigger than that. Smaller would be okay. Then you want something that you could submerge the pipe in, like a big bucket. Might work, or like I've got these big containers that used to have birdseed in them. That would work. A vase, maybe a big flower vase would work. Just some large container that you can fill with water that you could lower the tube in. And then what you want to do is see if you can produce a tone that will harmonize when you lift the tube out of the water like I did. And so what I found after a very brief search, that's not it. I'm not even in the right box here. Let me see. Would be, oh, yeah. This is called tone generator. You see that green icon there? Anyways, you generate a tone, and I can set it at 880 hertz. And I could just hold that over the tuning fork, and it would, and then I could set it at 238 hertz. Right, and so I don't need a tuning fork to at least experience the activity. I could generate any frequency I want here just using my phone. So if you have a smartphone, this app was free. It looks like it's being paid for by solitaire apps on the bottom, just like every other thing I ever download, because they must think that I want to play solitaire nonstop. There's 928. Ooh, that's hard. Can you hear this one? I can't hear it. It's at 22,000 hertz. Maybe your dog is going crazy. Oops. Raise your hand when you can hear it. Oh, that didn't work. There we go. That's 68. I can hear that. That hurts. That's 9,000. 12,000. Can you hear that? I know you can because I can hear it. I'm old. Now, I can't really hear that. I kind of know it's there because I'm the teacher. You probably can hear it because you're young. That's your fault. All right. Yeah. So please make an effort to try to find some materials just to experience the activity of getting that pipe to resonate by having a tone over it. Any tone maker will do that you have. And thank you.